Buddy, welcome to the last talk of the day. We have Grant Schoenebeck from University of Michigan, where he will talk today about mechanisms to procure information without verification. Thank you so much, Grant.
All right, great. So welcome everyone. So I'm going to talk about mechanisms to procure information without verification. And this is joint work kind of in this order with Noah Burrell, who's a PhD student of mine, and Yuqing Kong and Fengyi Yu, who have moved on. Fengyi is on the market now, and you should hire him. He's great. Okay. So I have a fair bit of motivation here. So the setting is information procurement. So we have some set of tasks that we would like answers to. And examples could be peer grading or peer review, maybe crowd sensing. So like how long is the line at It's a Small World in Disneyland right now, or surveys or crowdsourcing, okay? And for various reasons, you don't want to answer these tasks within a firm, right? So all these examples, it's hard to just hire some employees to answer them. So instead we have a crowd that's going to answer the questions for us, right? The problem with this crowd is that they need motivation. Okay, so they're not just going to work for free or not do a very good job. So we want to motivate them. A blessing and curse is that in these settings, they're indifferent to the outcome. They don't care what grade their friend gets. They don't care whether or not this paper gets into the peer review, or they don't care very much. So unlike an auction where you can motivate truth-telling by the outcome of the auction, that's not the case here. And that really differentiates it from some of the other settings that algorithmic game theory looks at. However, the agents are strategic, so they will respond to monetary payments. So we want to pay them money to elicit effort. In this talk, the tasks will not be spot checked. So we want to avoid spot checking the tasks. Oftentimes that is a good idea. You can do that. You can grade a few assignments and maybe measure how far people are, though even there you have to be a little careful, as we'll see. And the reason why is sometimes it's impossible if it's a subjective answer, and sometimes it's just not desirable. Like if you want to deploy pure grading broadly, if you try to get like gold standard pure graded questions and get them assembled and ready, it makes you not want to do pure grading to think about doing that. Okay, so we want to avoid spot checking. And one thing I do want to stress is that in this talk, I'm pretty excited about this work, and I think it really connects theory and application. And these applications aren't just like throwaway, especially pure grading. I'm hoping that this work can be used to have more widespread pure grading in the future. So I'm really trying to connect the theory with the application. So for example, in pure grading, students could get much more and quicker feedback, and it could really improve learning students. So the basic goals are that agents should not benefit from false reporting. Okay, we want them to tell us the truth. We don't want to incentivize them to lie. And also payment should somehow measure the quality of reports. Okay, and what does this mean? It can take on two meanings. One is that in expectation, if they work harder, they should get a higher payment. And this relates to motivation. If they work harder and they get a lower payment, they won't be motivated to work hard. But also, and this is kind of newer to this talk and a little less familiar to our community, we want the payments to be ex post representative of the effort that the people put in, or ex post representative of the quality of their feedback. We call this measurement integrity. Okay, and the reason is, in a lot of those motivating examples, we want the compensation to be fair. Okay, so for example, if you give a student an A 80% of the time and an F 20% of the time, that's not the same as giving them a B. Okay, even if it motivates them just as well, it's still not the same, because grades should have integrity. It should be reflected of the work that was put forth. They shouldn't just be randomized lottery tickets. Okay, so we want our compensation to be fair. Another example is, one way to kind of get this stuff to work out in theory is you spot check someone, 1 out of 1,000,000 times, and if they fail the spot check, you cut off their head. Okay, this works in theory. This is not a realistic mechanism that anybody can deploy. It's not going to work in practice. So that's another reason we want measurement integrity. Finally, it relates to detecting high quality signals from agents. which is sometimes useful if you're aggregating later. And this is similar, but not exactly the same as Raf's talk on Thursday. So I wanted to plug that. So don't worry, theoretical insights are coming. Okay, we'll talk about mechanisms with provable guarantees and a variational interpretation of mutual information. And I'll define what those fancy words mean. And I'll talk a little bit about how it can be applied more broadly to machine learning. So it's not even just information elicitation. And it'll give a nice broad theoretical framework and show the theory application is connected. But first, I'll dwell a little bit more on the motivation, intuition, and making it a little more concrete. I think the theorist will be satisfied to be like, this is a good Simon's talk. So let's build some intuition, okay? So the obvious solution is to pay the agents, some loss function based on some estimation of the ground truth. Okay. Does anyone see what the problem is with this? Like, if you just ask people to grade a paper and you paid them how close they were to the TA? Yeah.
They all say A, everything is great.
They can all say A, but what if you pay them, even if you pay them based on how far they are from a TA? What's a way that they can manipulate their report and win? They don't even need to collude. So one thing they can do is they can just hedge their guess towards the mean. So if you think about it, you have kind of a prior, and then you have a signal, which is a noisy version of the truth. And so you should hedge your answer back towards the ground truth. And this is not just in theory land, but actually this works out in reality. Okay, so this is data provided to us graciously by Jason Hartline at Northwestern University. And there's 4 semesters of data. And what we did is we looked at the mean squared error of the students, the average mean squared error of the student compared to TA, but the TA graded on these papers. And we did different ones, but for now, let's just look at merge, hedge, which is purple here. And you can see that if they just hedge their answer, which I think was 70% their answer mixed with 30% of the prior, that on average, their mean rank, if they just employed hedge instead of the truthful strategy, their mean rank amongst the students increased by about 20. And the number of students differs by semester. There's, I think, between 200 and 600 students in each semester. But in any event, it gets better just by employing the simple strategy, right? Where we did it ex post, not knowing anything about the data or anything about anything. Okay. This problem is compounded, and this is to Kostas's points, when you base you pay them a loss not of some external exogenous signal of ground truth, but based on the peers ID the ground truth. Okay, so here you can see that hedge, as more agents employ the hedge strategy, the increase that you get in the payoff for hedge actually increases, right? Because as the other agents are hedging, the more the other agents are hedging, the more beneficial it is for you to hedge. And in fact, it's kind of a ratchet, and you'll get back to the prior. So everyone will just report the prior. That's kind of the equilibrium in these games, which is obviously not what we want. So this data, I'll explain where this data came from in a little bit. This is kind of synthetic data here. So there's a strategic problem. And then there's the other kind of dimension we'll look at today is this measurement integrity. So again, we want the rewards to be kind of interpreted as a measurement of quality. Okay, so let me tell you where this data is coming from. Okay, so we created a pure grading model, and the idea of the synthetic data is you can know the true error, you can know everything. So it's very, very good for you. It's based on data from this paper by Pish et al. And they had a lot of, so it's looks like real data does. Okay, so how is their model created? Each submission has a quality, which is an integer between 0 and 10, and it's drawn from a binomial distribution, basically 10 draws with mean 7. Okay, and then there's 2 types of graders. There's the passive graders, and they get a kind of signal that's between 0 and 10 that's drawn again by a binomial with mean of the quality of the paper. And the active graders get a binomial, but instead of being based on 10 draws from this binomial, it's based on 30 draws. And we round it just so that it's in the same space, scores from 0 to 10. So the active graders have more information than the passive graders do. And the goal is, do these mechanisms do a good job of identifying who put in more effort, who put in less effort? Okay. So also some agents had biased reports, but I won't go into that here for the sake of time. And there's 10 assignments over the kind of semester, and each assignment is graded 4 times, and each student grades 4 other assignments. Okay. So that's the setup here. Yeah. Oh, yeah, Samina. Yeah, that's their impression of the quality of the paper. So they don't see the actual quality. They see a version that's kind of filtered through this noisy signal, this noisy channel. Yeah. Yeah, please do ask questions. All right, here are some mechanisms. I'll describe some in a little more detail than others, the simpler ones. So one is you can just take the mean squared error, easy enough. So you compare an agent's report to the mean of the other agent's reports. You can try to do a parameterized estimate of it to get rid of the bias of the agents. You can do output agreement, which is you pay them 1 if they agree with a peer and 0 if they don't agree with that peer. A modification of that by faulting Yurka and Radanovic is called pure truth theorem, and there it's like output agreement that you get paid if you agree and don't get paid if you don't agree, but how much you get paid is inversely proportional to how likely that outcome is. So you get paid more for agreeing on less common answers. DMI or determinate mutual information, which was in SOTA a year or 2 ago by Yuqing Kong, is another one, and I won't describe that one very much. And it's kind of a beautiful play on the mutual information mechanism, which I will describe. And then there's this talk, I'll talk in the second part of the talk about the pairing mechanism. And there's different versions of it. You can parameterize it, you can not parameterize it, and you can use different kind of scoring rules basically as part of it. And we look at 4 scoring rules. So one is total variation distance. And if you use that, it's the same mechanism as the correlation agreement mechanism by Snyder et al. And you can use KL divergence, you can use squared Hellinger distance, you can use chi-squared divergence, and you will see how this kind of fits in later. Okay. And then what we did is we measured the area under the curve for using the payment as a classifier, right? So each agent is either active or passive, so we can classify them. So we use the score of the mechanism as a classifier for the agents as active or passive, and we'll measure the area under the curve.
So can I ask a question about the setting?
Yeah.
Do you assume you know you have a prior over scores, like you know that kind of like this curve of scores, and you use it actively?
Do any of these mechanisms use the fact that like we kind of know what the scores should be?
I mean, it sounded like the peer truth serum uses it in their description.
Yeah, so they use it and they kind of learn it over time what the distribution is, and they use the distribution in the past to kind of pay the present round.
Right.
So that one is a little more complicated and the other ones don't. So here we vary the number of assignments per semester. So here you have kind of less information. Over here, you have more information over here, but it doesn't change too much. You see mean squared error is doing pretty well in predicting who's active and who's passive. The next best are the pairing mechanism, the parameterized pairing mechanism with KL divergence and Hellinger squared. And then kind of there's a group down here, that perhaps are at least led by output agreement and the total variation distance. Did I see a question? Yeah.
The problem is that you want to come up with an error metric to figure out who's active data and who's a passive data.
Right. Right. So we're just looking at the scores, no TA information or ground truth, and we want to figure out who's active and who's passive. What we really, I mean, this is part of measurement integrity, so I'm disentangling these 2 things. One part is strategy proofness. We'd like these to be robust against manipulation from the agents. And the other is that we're assuming the agents are reporting truthfully. And in that case, in that very simplified case, where everyone is reporting truthfully, do they even work then? right? Here we have the simplified case. We're asking everyone reports truthfully. Can I tell who's active and who's passive, even if everyone's reporting truthfully?
But the other ground truth wouldn't like any permutation of the outcomes of the given equilibrium that we could coordinate to just flip the sign of this port.
Yeah, you can have opposite state, right? So that you'll get multiple equilibria here, and I can talk more about that or glide over it. You can certainly have opposite state. I don't think opposite state is a big problem in reality, but certainly there are multiple.
The scaling of the whole thing is not well defined, then, right?
So yeah,
Like I don't know, we could just shift the entire distribution of scores or all kinds of things.
you can try that. That won't actually work, and we'll kind of see why.
So for things like output agreement, how many categories do you have?
Right. So here there's 10, right, or 11, I guess, because it's 0 through 10.
Oh, I see. So we're in that example that,
Exactly.
wow, I'm surprised it did that well.
Yeah, some of these are do pretty well. Yeah. Great. Thanks for all the questions. So we have kind of maybe 3 classes, maybe 4 classes there. And now we'll use the same data and we'll look at strategic deviations. So we consider these. So everyone reports 10. This is everyone gets an A. Common issue if you actually use pure grading in classes. Report the prior, that would be everyone reports 7. Hedge, we talked about that before. Fixed bias, I'm going to leave that out. They do some heuristic to try to fix their bias. Add noise, they just take their signal, add some noise. Merge signals. So here, maybe output agreement on 11 signals is kind of rough. So they'll merge into kind of good, bad, medium, good paper. Okay. And the y-axis is going to be the average gain in rank from strategic manipulations. So you can see, not surprisingly, that if you use the mean squared error, that a lot of these strategies, very simple strategies, actually do yield an increase in rank by the people that employ them. Okay, and so that's mean squared error. This is output agreement, which is also very susceptible to these strategies. And then this is the pairing mechanism with the Hellinger squared and the Kale divergence, which are pretty resistant to strategic manipulation. Here you can see if over 70% of the people are reporting all 10, then that's what you want to do there. And here, even at that point, that strategy, none of these strategies help you with the Kale divergence. Okay, so this doesn't mean they're strategy proof, but it is kind of interesting to check it out in more practice than theory. Okay.
So how does it break that? I mean, all 10, I mean, what do you learn? I mean, what is that? Like, everybody says all 10, like, what is, oh, you don't go quite to 100, you say like 9, 6 flips after 9. I mean,
Like here, why doesn't it flip?
yeah.
We'll see.
Yeah.
We'll see. Yeah. Maybe more surprisingly, and I'll talk about this a little bit, is that these things, some of these mechanisms actually fail. They have some theoretical guarantees on them, but they're actually not strategy proof in our example here. And yeah, so let me talk about that now, I guess. So a lot like above 0 is kind of good and below 0 is kind of bad as a heuristic here. And how far you are above or below doesn't matter that much. How far you're below means how far manipulating helps, but how far you're above just means how much manipulating hurts you. So anything above 0 is kind of equally good. And we see that a lot of the mechanisms that have provable guarantees are above 0, but not all of them, right? So for example, output agreement has some provable guarantee, it's truthful, but the guarantee only holds with some priors. And I guess it doesn't hold in the priors that we're using. And the pairing mechanism, as we'll see, it's strongly truthful, but it's epsilon strongly truthful. And what that epsilon is, depends on the situation, and epsilon's pretty big here. It's not helping you very much, right? Overall, you see that the maximum measurement integrity is gained by algorithms mean squared error, which are easy to manipulate. But we can these algorithms do a pretty good job trading off measurement integrity and strategic manipulation. So they do pretty well, but not as well. So it seems, at least with the mechanisms we have, there is some trade-off. We tried really hard to get rid of the trade-off, or no, we tried kind of hard to get rid of the trade-off. and we did not succeed. Any questions there?
So for the definition of measurement integrity, you would like the randomness of the process. What's how much variance I have in identifying somebody that what is?
Yeah. So okay. Right. So this is a conglomeration of a lot of results from a paper. We use different forms of measurement integrity. Which form of measurement integrity you want probably depends on the situation. So the one I showed you is area under the curve. You may want to do like a Kendall Tau distance from some ground truth ranking you have in a different situation, or measure the actual like some metric of distance. So you can kind of put your own thing in here, and this is an average of a bunch of different experiments.
Yeah, actually, I have a question about this. So this is one. Is this representative of a wide class of examples, or like how should I be thinking about this?
I would say it's representative of a wide class of examples that look a lot like the example I showed you. Okay, so a few features that example has is that there's not a lot of data there. Okay, so each person's grading 4 assignments. If you have a lot of data, they'll all work really well. But again, the application areas that we're thinking about in peer grading, it's not realistic to have people grade the same assignment 20 times. I mean, 4 is pushing it perhaps even, right? So I think these results would be fairly robust in the kind of similar environments with not a lot of data, about the same number of points, things like that. Okay, so now we get to the theory part. So we're going to talk about the mechanism design, just the setup, then mutual information, connect mutual information to variational statistics, show how that reduces to a learning problem, and then relate it back to measurement. So in our model, we have this joint distribution, D, and each agent gets a signal drawn from D. Okay, so they're correlated, right? It's stochastically relevant, which just means the signals there's some correlation there. They're not completely independent of one another. Okay. Based on their signal, they give a report to the mechanism. They can lie, okay? And the mechanism then looks at all the signals and gives everyone a payment back. The agents are trying to maximize their utility, which is their payment minus the effort. We won't think about effort much in this talk, but it's an interesting topic. And the key assumption we're going to make, or one key assumption we're going to make, is that the payments only depend on the reports, no external information. Okay. We'll be in the multitask setting, which means that this whole operation is repeated several times in parallel. So it's not just one paper you're grading several assignments, and that's going to be important for our mechanism. Okay. The multitask setting was first put forth by Dasgupta and Ghosh, so that's quite nice. Okay. So I've switched notation to X's and Y's. So Alice gets some signals, which may be her commute time on different days. Bob's gets some signals, which is his commute time on the same set of days. Then they put forth a report, which is some strategy applied to their signals. And the payment is based on their reports. One assumption that we're going to make, a key assumption, is that the strategy, the way that Alice and Bob manipulate their signals, is they apply the same strategy to each signal. So example would be merge or a hedge, where I apply the same strategy to each signal. They're not going to, for example, switch their first and second signals. We're not going to let them do that. Again, the goal is we want a strongly truthful mechanism, which we'll call it strongly truthful if the truth telling is a Bayes-Nash equilibrium, and it has the highest payment. Yeah.
So this has to be like an adaptive algorithm. So
it's going to be a one-shot game here where this all happens at the same time. So they can't do something adaptive. But they do know the distribution D. They kind of have all the information they need to try to goose the mechanism.
Because this mapping is from the signal space to the report space, I should think of it as a fixed.
Think of it as a fixed mapping. It can be randomized, so they can take half their answers and run hedge, and half of them report all 10. That's completely allowed, like a mixed strategy like that. what they can't do, right, really is like take the first two answers, add them together, take the second, third, fourth, and divide them. So they can't combine answers. Okay, and what I'll show is that we can incentivize agents to report truthfully. This works in a very general setting with heterogeneous agents and very large spaces of report spaces, which has not been done before. It works well as a measurement, and it reduces kind of mechanism design to learning a certain reduction. And the way it does this is it kind of learns the geometry of the space. It learns which signals are which pairs of signals are close and which ones are far. Okay, and this is why you can't just have opposite day and random permutations, because it's actually learning some geometry of the space. All right, so mutual information. Okay, so we would like that the payment the mechanism gives them if they tell the truth is greater than the one it gives them if they lie, right? And we can represent this in the kind of machine learning notation that I hadn't seen since grad school, which has been a while. So we have different panels here, all right? And so over and over again, Alice and Bob get a signal from this joint distribution, and they push it through, Alice pushes it through her strategic channel, basically to get X hat, Bob pushes it through his to get Y hat. So we can write this, and we have a Markov chain, because Y and X hat are independent conditioned on X here. So we have a nice Markov chain. And what that means is that we can employ this data processing inequality. This is something that may be new to computer scientists. Double E people know this backward and forward. I'm in the computer science variety. Okay, so what it says is that if you measure the mutual information between two variables and you take one variable and you apply some function to that variable, your mutual information can only decrease, cannot increase, right? And if you take the mutual information between X and Y, it's greater than the mutual information Y and X hat, which is greater than the mutual information between Y hat and X for the same reason. Okay. The mutual information is defined this way. So this is the useful one part for here. So it's the distance, the KL divergence between the joint distribution between X and Y and the product of the marginal distributions. So in this one here, we basically force X and Y to be independent because we're taking the product of the marginals. And here they are dependent and saying, how much dependence do they have? How far is the joint distribution from the product of the marginals? And this, if you write it out, and it looks like that. And we'll use this later, but I'll explain a little bit more. Okay. So the mutual information framework, which Yucheng and I came up with, says just pay Alice and Bob the mutual information between the reports. And as long as this joint prior is stochastically relevant, then M is strongly truthful, right? Because employing any strategy will only decrease your mutual information, which will decrease your payment. Okay. So go. You can extend this, interestingly. You don't have to use the normal mutual information, which is defined with the KL divergence. You can use any phi divergence. These divergence just measure the distance between two distributions, and you can use any of them to measure this distance, and this will work out just as well as before. So two particular ones would be the KL divergence and the absolute value of X minus 1, which gives you the total variation distance, which, as I mentioned before, is equivalent to the correlation agreement mechanism.
So it's for a discrete distribution across the components of the reports?
It doesn't have to be discrete. It's just you can measure mutual information of any two joint random variables, X and Y. This is right. So right, that's the next question: is where the heck do we get the distribution from? We only have draws from this thing. Okay, so that's you're 4 slides ahead of me. So I will get there. But first, for the people who are less familiar with this, I have some examples of computing mutual information. So we have Alice and we have Bob, and they're flipping a coin, and they're both going to look at the same coin. Okay, so maybe, so with half probability, the coin lands heads, with half it lands tails. If it lands heads, they both report heads, tails, they both report tails. The product of the marginals, well, Alice sees heads half the time, Bob sees heads half the time. So the product of the marginal is just a uniform distribution over the outcomes, okay? So again, we're paying them the mutual information, which is the KL divergence between the joint distribution and the product of the marginals. These are different, okay? So they have a distance that's greater than 0. This example here, Alice and Bob are looking at their own coin, right? They're flipping their own coin and reporting it. So in this case, the joint distribution is, and the product of the marginals are both uniform. And here they're the same. And so the distance between them is equal to 0, right? Which is good because intuitively they have no mutual information and we shouldn't be paying them anything. And the third example is the coin is just heads on the ground. They're both looking at the coin. It says heads, okay? So the joint distribution is they both see heads all the time. Product of the marginals is they both see heads all the time because individually they both see heads all the time. And again, these are the same. There's no distance between them. So the mutual information is 0. Yeah.
So you're assuming that their observations are the only shared randomness they have?
Yes. Yeah. Right. So here, the way you map this on is they're looking at a picture of a dog and a cat, not a coin. And you pay them mutual information to try to get out whether it's a dog or a cat. If they report truthfully, they'll have positive mutual information. If they just report randomly, they won't have positive mutual information. And if they report the same thing all the time, they won't have positive mutual information. So that's some intuition for why the mutual information should work. It's obviously a lot more general than binary. You can do it on crazy things, and we'll see how to do it on crazy things in a few slides. Yeah.
So I guess getting back to my earlier question in terms of the scaling without the ground truth, this kind of incentivizes them to have a uniform marginal distribution across the.
Yeah, no, because remember we have the data processing inequality. So for any scaling that they do, they're not actually going to be able to improve their mutual information, right? If Alice and Bob both apply a function, so they have right here, so they report some function of their distribution, as long as the gentleman back pointed out, as long as the only shared randomness that they have is via this distribution, they can't increase their mutual information via scaling or anything like that. So it's different from entropy, and we'll.
So that assumes the signal space is as rich as the state that you observe, or.
Yeah, we are assuming that the signal
So
space.
it's like there's a continuous quality of the assignment that have 10 grades that would apply.
Right. Yeah, and we can deal with the continuous case here. That's coming. Not yet. Yeah.
What if they say the truth half of the time and are random half of the time? How do you differentiate from?
Oh yeah, if they're truthful half the time and it's random half the time, then you could fill this out and they get a non-zero mutual information, but it wouldn't be as much as them being truthful all the time.
So like what is, so you know the exact quantity of mutual information?
No, but what we saw is that if they tell the truth, they're going to maximize the mutual information. So they could lie, but it will decrease their payments. So you don't actually know how much you're supposed to be paying them here if they're truthful, but you do know that you're maximizing the payments when they're truthful.
So let's say all lie, do we still have shared randomness?
So it depends how they lie, as we see here. So they can lie by looking at their own point and flipping it, in which case they're going to get paid 0. They can lie by always agreeing, in which case they're going to pay 0. They can lie by permuting by doing opposites, in which case we're not going to catch them in our setting here. In this setting. So a big problem is how do we compute the mutual information? All we have is a few draws from this distribution. We don't have the distribution itself. And if you have a small finite number of reports, what you can do is just use empirical distribution and hope that it's close. Okay, so you don't know the actual distribution, but you just say, okay, instead of the actual distribution, I plug in empirical distribution. Okay, how many times do Alice and Bob both report heads? So the point here is that you have this mutual information. it's some function, okay? It's some function of the joint distribution, the product of the marginals, which is just to say, how often do they both say heads? How often does Bob say heads and Alice's tails, et cetera, et cetera. And you can just plug in an empirical distribution that you see, okay, 30% of the time Bob said heads and Alice said tails. So I plug that into the formula and I just report that. And you can get good Chernoff concentration bounds here, right? So you don't lose that much. With 4, you're going to lose quite a bit, but generally it's going to be long. Okay. So that's one thing you can do. So in this example here, the true distribution is 50-50, but instead they saw heads 48% of the time and tails 52% of the time, and so I think I'm going to just skip this. So you plug this into the formula here, and you end up adding 5,2 and 5,0. So truly you should add 5,2002 divided by 4. You should get 1. So their payment should be 1 here. But in fact, you're a little bit off, but not too far off. So why aren't we done yet? And one reason is that the goal is too loose. So truth telling versus random may not differ by very much. Okay. And the way to solve this normally is you just rescale the payments. So that truth telling pays 1 and say 0. If they answer randomly, they get 0. And you say, hey, we're done. Okay. But in practice, this doesn't work very well. So one issue is a lot of times you have limited liability. That means you can't give negative payments. So if you have mechanical turkeys, you can't, this is Costas from this morning, the hunters never get eaten by the bears here. Okay. So there's no negative payments. Also, this works poorly for risk-adverse agents, as I discussed earlier, where the payments get really large and really small, and it doesn't necessarily work well as a measurement. Okay. Also, what we did so far requires finite x and y, and the convergence depends on the size of the report spaces. Okay, so we want to do more. So we're going to use variational statistics. Okay, so what we're going to do is we're going to rewrite the mutual information with hitherto looked like this inscrutable integral as this equally inscrutable optimization problem. Okay, so we're going to scrutinate it. Okay, so what does this say here? First, notice this is an expectation over the joint distribution. This is an expectation over the product of the marginals. We're going to have a function k here, which we want, it takes in pairs of reports and produces a real number. We want that to be big on the right-hand side. Oh, my little guy is going. Big on the right-hand side, large on the joint distribution, but somehow small on the product of the marginals. Okay. Notice there's not just k here and k here. This k is put through this phi star. Phi star is the dual, the convex dual, which is defined thusly, which is another somewhat inscrutable formula that we'll examine a little bit. Okay. So what we want to do is we want to replace this thing here by this optimization problem. We're going to optimize over k. I'll explain why in a second. Okay, but first let's see just briefly how to do this. Notice here we have phi and here we have phi star. So we want to kind of replace phi with phi star. Here we have an equation for phi star, but not for phi. Okay. So these convex duals define phi star this way. Then you can take what I did here is I took the dual of the dual, right? So the formula for the dual of the dual is just this. You just take this formula here and you plug in phi star for phi, which I did there. Okay, so that's the dual of the dual. And the Fenchel-Moreau theorem says that well, first, it's not too hard to see, I guess, that the original function is always greater than the dual of the dual. And actually, they're equal if phi is convex, which is always the case that we're going to be here. So the original function equals the dual of the dual, which means that the original function equals sup ak over k ak minus phi star k. Notice that, see here, this equation and this equation here, the only difference is where the star is. Here the star is there, and then it just moved over it here, right? And that's why they're kind of duals. All right, this is sometimes called the Fenchel dual inequality, and we'll assume that phi is differentiable. And if it's differentiable, then we know how to optimize this. K, the supremum K is going to be K equals the derivative of phi at A. Okay, so now what we're going to do is we had this thing here. It has a phi in it. We're going to take the inside of this integral and kind of rewrite it with our dual formula. Okay, that's what we're going to do here. So this is the inside of the integral, which I put here. We take the phi and we just replace with this formula. Okay, so we get the supremum over K. I'm subscripting K because we're going to have lots of Ks. So I'm subscripting the K with XY. And then we have the supremum of this is the joint distribution divided by the product of the marginals, which is kind of what was in there, times K minus phi star of K. And then we have this, the density of the joint distribution, or the product of the marginals on the outside. This happily distributes, right? So these are going to cancel here. And that leaves us with the supremum over K XY of the density on the joint distribution minus phi star of K times the density of the joint times the density of the distribution of the product of the marginals. Okay, so this is what we have. It's maximized at this value here, which I'll say, I think, more about in the next slide. All right, so let's just replace the inside here with what we had previously. We get this formula here. This is an integration over d over x and y. And what we'll do is we'll just take the xy outside kind of the integral, and now we get this formula here. So it's a supreme over xy. So again, K assigns a value to every pair of signals, and it should be kind of big on the joint distribution and relatively small on the product of the marginal distributions. Okay. And equality holds when, so that the supremum equals the mutual information, when this K function is this thing here. Remember, phi was convex, so phi prime is monotonically increasing. Right? So this says this is the density on the joint distribution. This is the density on the product of the marginals. So as the density on the joint is large relative to the density in the product of the marginals, this is big, and so phi prime of this is larger, and so K is larger on those values. Right? So that's how we're optimizing. Okay. So that is the variational statistics. One way to think about this, to make sense of it, is that it turns mutual information into an optimization problem. This K can be thought of as a distinguisher, right? So you have 2 points in space, and depending on how you look at the points, they can be closer together or further apart. And that's kind of what the distinguisher is doing. If you look at them kind of the wrong way, they look very close. If you look at them the right way, they look far apart. You can't make them look further apart than they are, right? So this distinguisher, if you use a lousy K, the joint distribution of the product and marginals look close together. If you use a really good K, they look the correct distance apart, but you can't use a K that makes them look further apart than they are. Okay, and that's important for us here. And if you kind of use the right K, you get a plug-in estimator of the mutual information, right? So if I know what K is, then I can just take some draws from the joint distribution, take some draws from the product of the marginals, and I'm going to get an unbiased estimator of the mutual information. And so this is exactly what our pairing mechanism does. Okay, we take draws from the joint distribution, subtract off, apply K to it, subtract off phi star of K applied to some draws from the product of the marginals, and this is the payment. Okay. And how do we get draws from the joint distribution? Well, we have a bonus task, and we just take Alice's and Bob's report on the bonus task. And how do we get draws from the product of the marginals? Well, we have a penalty task for Bob and a penalty task for Alice. We make sure they're not the same task, right? And we take Alice and Bob's reports there, throw it through K, and apply phi star to it, and that's what we pay. Yeah.
Could you describe how this relates to optimal scoring rules when we have noisy measurements by ground truth?
So this is different because we're measuring the distance between the joint distribution and the product of the marginals, which is just a different thing than scoring rules. Because here we have Alice and Bob, and there you just have Alice and ground truth. There's no ground truth here. There's just Alice and Bob.
There you have like a noisy measurement of the ground truth, right? And here it's almost like Bob is like a noisy measure of the ground truth if Bob is truthful.
There doesn't have to be a ground truth here. So this will work when there's no ground truth. We could ask for opinions on things where there's no ground truth. So I think it's rather different from the scoring level. So,
What's the variance of this system area?
well, obviously, you're going to kind of average over all of these things.
What
So
is K for various known?
what is K?
What is K? Do you have it? Yeah.
Oh, we have it in our papers written out. I can't remember what it is. So I have a picture later on. So I do have a picture, yeah. So we'll see K for the total variation of the tail versions, I think. So so the pairing mechanism, this is the payment function, is just K applied to what we get from the bonus task minus phi star of K on the penalty task. The expected payment of this is is equal to, they could lie in their reports, right? They don't have to report truthfully, but no matter what K we use, this is upper bounded by the mutual information between X hat and Y hat, which is bounded by the mutual information between X and Y by the data processing inequality, okay? And if we use the right K, if we learn the right K to optimally distinguish these two distributions, then they're paid the mutual information between X and Y, right? So this ensures us, if we learn the right K, that we can pay them the mutual information between X and Y, and no matter what they do to try to goose us, they can't get more payment than that. So what this means is that to get an approximately truthful mechanism, what we need to do, and I'm sliding a lot under the covers here, is approximate the ideal distinguisher between under the truthful strategy. And this involves solving this optimization problem here. And that takes us to the learning part, okay? So we need to solve this optimization problem here. If X and Y are finite, this is easy. We know how to do that. But what if X and Y are not finite? Then you can, for example, restrict K. Like we could assume that X and Y are Gaussians, and then we know the family that K should be from, and then we can optimize K only over this family. Okay. And this is necessary if X and Y are infinite. Otherwise, we're going to overfit in our learning K. But it can give you improvements even if X and Y are finite. Okay. Because if we can restrict what K is, we can avoid overfitting and get better estimates even for finite X and Y. So this is known as an empirical risk minimization problem in machine learning, I'm told by Feng Yi. And so this really, and machine learning people study this a lot, know everything there is to know about it, or not everything, but a fair bit. And so, for example, K could be a neuronet, and then we could, run machine learning neuronet things and perhaps learn for a very large set of K how to optimize this, how to find an optimal K for a very large class of hypotheses. Okay. A slightly weird side note is that the agents want the mechanism to learn a good K. And in certain situations, and this is what we saw on the first summary slide, agents can help by lying. If they can lie to help the mechanism learn K, they can improve their payment. Okay. So an example would be if we're overfitting and not learning this K very well, they could group their answers together, and we'll learn a better K because it's easier, because the space is smaller and it'll overfit less, and then they'll actually improve their payment. So that's kind of a bug. If we don't have enough data, we need to kind of regularize properly. So this is really neat, and what another really cool property here of this mechanism is that so far we've assumed that there's Alice and there's Bob. Okay, and they answered all the same questions. Now, in the model I gave you at the beginning, people did not answer the same, they did not grade all the same problems. They graded a random set of 4 problems, and we wanted to pay them. So what we're going to do here is imagine X is agent I signal, and Y is every other agent signal. Okay, now we want to pay the mutual information between I's signal and everyone else's signal. How are we going to compute that? This is a big space. We certainly can't like just look at a matrix. Okay, so all we need is the probability of X conditioned on Y and the probability of X. And that's enough for us to compute K of X, Y, which is all we need to run our mechanism. Okay, why is that? Well, what we need is the ratio between the joint distribution and the product of the marginals. Phi prime of that, we know how to compute phi prime. And this is just equal to the probability of X conditioned on Y divided by probability of X. So what we can do is we can learn some soft predictor. So we take half the data, split it out, learn some soft predictor to predict X agent I signal given everyone else's signal, and to predict a distribution over that. And then for the particular Y, we plug that in, we get a distribution over X's that we've predicted. We choose the X that Alice actually reported, and we get probability of X conditioned on Y. Okay, and then we still have to learn probability of X. So technically, for the strategic guarantees, you have to guarantee that you're learning the soft predictor correctly. Okay. But that's why in our little practice agent-based model, it seems to work pretty well and for the parameterized mechanisms. Okay. So why is this working a little bit? Well, so we have this scoring function here. Equality holds when we have this K as this ideal. Well, what does this ideal thing look like? Did I lie? Do I not have? Oh, I don't have the right answer here. I can look it up after the talk. Sorry. But so we have Gaussian's joint distribution between Alice and Bob here. And then we have, this is if we use this convex function, A minus 1 absolute value, then there's kind of two sections, and Alice and Bob are kind of paid 1 if they land in the same section and minus 1 if they land in different sections. That's kind of how the payment works. And notice that there's kind of good things about this payment, and that doesn't have long tails, can't mess up too badly, you're just paying them 1 or 0, but it's also not particularly nuanced, right? If we take the KL divergence, we get a much more nuanced payment system that scales with exactly how much they agree. However, on the tails, maybe you can mess up a little bit more. So one just quick philosophical comment is that a lot of the previous work, like the pure truth serum, tried to create simple mechanisms that you could explain to people. This work is taking on a different sort of quality. We're giving up on simplicity and explaining the mechanism, and instead we're getting measurement integrity. This might be good, for example, if the agents can't really reason about what's happening in the mechanism anyhow, and they try it out and they say, oh, I worked harder this time and I worked less hard the next time, but I got paid more when I worked less hard, so I don't believe this mechanism, right? So you may want measurement integrity for agents kind of trying things out. This is related to the dynamical systems talk that we saw this morning. But there's a kind of a different philosophy that's going on in this work versus previous works. Okay, just to review so I can show my picture again. So in the finite case, you can just minimize the empirical risk minimization, or you can split the data and kind of learn K on part of the data, apply it to the other part of the data. And doing this, you can restrict the space. We can apply this even if the agents don't answer the same questions. Okay, we can use different fees in our feed divergence, and we look at total variation distance, KL divergence, squared Hellinger, and chi-squared divergence. Okay, so this is just a reprise of this slide here, so you can kind of see that the parameterized one, when we had H, we had Hellinger squared, did the best on measurement integrity, followed by the KL divergence, and these both had very strong strategic properties. When we don't parameterize, we're overfitting, and strategic deviations are helping. And again, those deviations are ones where the agents are helping the mechanism learn the correct K. So let me just talk briefly about some future directions. So one would be more rigorous study of measurement integrity. We have agent-based models. It'd be nice to have math. There is a budding science of this for proper scoring rules that people are starting to do. This is a harder setting. we assume that agents are strategic in practice. They may not be strategic. You can imagine your students, some of them are going to try no matter what. Some of them are going to be strategic. Some of them are just out to lunch. Some of them want to mess up your class because they don't like you. Okay, so we might want to be robust and not assume that all agents are strategic. We have work on that at WWW last year. We may want stronger truthfulness guarantees besides epsilon strongly truthful. So for example, Yu-Ching's DMI mechanism obtains much stronger guarantees, but it doesn't work very well for measurement integrity. Maybe there's a best of both worlds to be had there. Snyder et al. In their correlation agreement show a setting where basically it's reasonable to assume that you know K a priori. So you know this distinguisher, and assuming that you know it, you have this unbiased estimator and you get kind of stronger guarantees. We didn't model effort very much here. I have ongoing work kind of trying to take effort more seriously, how to get effort, how to incentivize effort from people. We looked at this multitask setting that requires that you have different tasks that you're evaluating. You can also look at the single task setting where you only have one question at a time. That's obviously a little harder. You tend to ask agents for a little bit more information about what they think other agents are going to report. And there's work on that. And finally, there's work on the cheap signals. So you notice that Max said, well, what if the signal space is richer than the report space? That can be a problem. So you can imagine agents decide they're supposed to be pure grading based on the quality of the essay, but they're just grading based on how many grammatical errors there were, right? So there's a cheaper signal and it's easier to agree upon. And if you pay the mutual information of that cheap signal, it's going to be greater than the mutual information of the signal you're actually seeking, which is a problem. We have solutions to this that are maybe not fully fleshed out yet. And also you could try to combine them with TAs and some ground truth checks. But this is still a pretty active and interesting area of research. So lastly, there's lots of applications of it. You can relate it to machine learning and the noisy data problem, which I won't talk more about now, to social choice. And Jamie Morgenstern has a nice paper on arXiv suggesting how to apply this stuff to peer review. And my favorite one though is peer grading. And I hope that this stuff really works in real life, and we can help students learn better. I feel like we really are getting close, and there's really not that many hard theoretical or not unassailable theoretical challenges. Yeah, there doesn't seem to be any big roadblocks, but there is neat theoretical work remaining to be done, and I'd be happy to talk to people about that in the rest of the workshop. So thanks.
Okay. Thank you, Grant. So we're opening up the floor to questions.
Very interesting stuff. So I guess I have a more high-level question about the application. So like, what are the in your opinion, the big challenges in actually a system that works, like in view of all the work?
Yeah, so I think there's two. So one is integrating. So we have TAs, we want to integrate them, and I think we can integrate them to kind of help deal with the cheap signal problem. So how to do that? I think that's one big one. The other big one, which I haven't thought about so much, I think it's somewhat straightforward, but I'm not sure, which is we don't want to just elicit numerical grades from people. We actually want good feedback, right? And the question is how to get good feedback. And for example, in peer review, I think you can just rate the feedback, right? Because you're in a good situation where you're already supposed to have read everyone else's review anyhow. So now you just need to give the reviews a numerical score, which will then itself be part of the system. Are you accurately grading the reviews of other agents? So I think those are the two main things: is a cheap signal, and then we don't want to just elicit a number. We want to make it into a system.
And a follow-up question. I was always curious. I mean, like, I guess, like maybe you're teaching class at a place where people are reasonably strong. Presumably, there are scenarios where you have to study the trade-off of how much effort the TA has to put in given the expertise in the audience, to get a reasonable signal out of the.
Right. So, teaching a kind of intro theory class, one feeling I've had is that it should be easier to grade the problems than to do the problems. Because if a student can't recognize a correct answer, they certainly can't get a correct answer. So I haven't seen the peer grading literature about this, but my hope is, one, that peer grading is pedagogically useful. People learn stuff from peer grading. And two, that it's actually slightly easier to peer grade than it is to do the problem. Because as you point out, you have a diverse range of students. We love them all. And some of them are better at the work than others. And how well can you put people who don't quite understand what's going on and have them grade something is an open question. Yeah.
I just have a question about the application. So I thought that in some places you have to pay the students before, like the TAs before, like, don't you pay them before they do the work? So do you have to then give them some bonuses based on the quality of the work, and how large do those bonuses have to be related to the baseline?
Oh, the idea is that this would be employed for students, grading other students. For the TAs, you kind of assume they're in the firm and are doing a good job. You can double check their work, perhaps,
okay,
doing
so
this, but the idea is not to compensate TAs based on the quality of their work. That's not, that will violate all kinds of union things. For an example, and this is in Jamie's paper too, by grading other students' assignments, you may be able to get your own assignment graded, and maybe you can turn it in as many times as you want to, until you're happy with the peer grade result, and then you turn it into the professor to be graded. And so the reward they're getting is not monetary here, which is not going to work with students, and maybe not even based on their grade, but based on how many times they get some benefit of turning in their own assignment. So they get some useful utility. And it's the same in peer review. We're not going to pay you money to peer review. We're going to allow you to submit 17 papers to NeurIPS instead of the normal 2.
I have a question that has to do with maybe issues of bounded rationality. So for example, like in mechanisms that may give like very fine-grained like payoff differences, maybe that's not something like that meaningfully registers on the student, right? So how, like, could the theory somehow like account for some behavioral models like that?
Yeah, I mean, that's one of the motivations behind the measurement integrity, is that if the signal is very noisy, right, and I try hard on one and I try less hard on the other, and I can't pick up any signal in the feedback I get back, that's a little disheartening. If measurement integrity was perfect, it would perfectly pick that up and be able to say, oh, you slacked a little bit on this one, we noticed that. So that's one of the motivations of measurement integrity. So there's, I think empirical question of how much measurement integrity do you need to get this to work, and how much do people need to grade to get that level of measurement integrity? But certainly that's one of the motivations behind measurement integrity.
But this question, have you even tried to test it in a simple, like a multi-agent model, where you say like, okay, I make this assumption about how people respond, and then
yeah. So we have the area under the curve thing, and it took us a fair bit of time to figure out to disentangle the strategic part of it from the measurement information part of it. And we could definitely, as a follow-up, kind of run more synthetic experiments where agents are trying out different strategies of working hard or not working hard. Actually, there's a paper by Raff that does something very similar to this using replicator dynamics and some of the peer prediction mechanisms, but it doesn't have the latest and greatest mechanisms in it now.
Okay. Any other?
Yes. It seems like in this setting, in order to estimate the mutual information, you need multiple graders to be grading the same student's work. But you might also have a trade-off where you maybe have a limited supply of graders and you want them to grade as many distinct works as possible. So is there work on?
There
that
is some
trade-off?
work on that. Yang Liu and Yuling Chen had a paper, and I think there's work that I'm less familiar from databases on that. And their solution is to kind of use a machine learning algorithm to try to learn the features, and then use the machine learning algorithm to kind of. So you're going to predict. It's back to the multi-agent setting here. Essentially, wrong one. Lost it. Where did you go? Where you're learning this, where all you need is a soft forecast for X's for the X. And so you don't need people to have graded that particular assignment as long as you can get a forecast. So maybe you can use a machine learning algorithm to do that. I think there's more work that needs to be done there. For example, are these grades predictable? Because they may be more predictable due to the flaws in the machine learning algorithm that people can kind of pick up. Machine learners not going to know this, but they are going to know that. It's an interesting research question. It was in my last grant proposal, but I haven't gotten around to that one yet. But yeah, there is some stuff on that, but it's not there yet.
Last question.
Thanks for all the great questions.
Thank you. Thank you. This we're done for the day.